So let's go back to our Hydra panel, and let's now talk about the function for setting of the water demands. In Urbano Hydra, you can set up water demands using many different methods. And now I will show you almost all of them. And then you will see what of those methods are good for you, what are useful for you, and which one will you use. So first of all, we have one method that we call percent calculation. And basically here in this part of the software, you can create any amount of these consumption categories, any amount of these demand configurations. So, and you have many different methods. So you can even combine different methods and then get the total calculated demands. So first of all, let's check this inhabitants in percent. So percent method. I will add a new configuration and I will call it people. So people living on this area, doesn't matter. And you have again your selection options. So you can set up where these demands will be set. So by default, you see the whole system is selected. And here you see that you can define water consumption per one inhabitant and actual number of inhabitant, or let's say number of people living on some area. So this is related to selection. So is it 1,000 people to the whole network, or let's say 1,000 people just to some parts of the network? So let's say that this main pipeline will be our main distribution network, where we will have no water demands, and then we will have our water distribution network where we will have our water demands set. Again, you have different selection options. You can use Urbano selections like branches and arrays, or you can use CAD selection. I will use this selection of arrays, and I will select this horizontal arrays and this for vertical arrays. So this part here, including these nodes on the main pipeline. So starting nodes on the main pipeline. And here I will say, okay, in this part of the network, I will have water consumption per one inhabitant per 1 day will be 180 liters per second per liters per day per inhabitant. And actual number of inhabitants, I will put it 5,000. Okay, population increase per year and design period. So this is the percentage each year, the starting number of people will increase during the design period of 30 years. And we have our coefficients of variation. This is the coefficients to calculate the peak daily flow and coefficient to calculate peak hourly flow. You can define any coefficient. I will leave the default as 1.5. So like I said, during the 30 years design period, if each year the starting number of people increases by 2%, we will have at the end of the design period this amount of people, so 9,056 people. If you don't want to use this method of increasing the number of people, just define the design period to 0 or population increase per year to 0. And then if you multiply this number with the water consumption per inhabitant per day, you will get average demand per day in liters per day. Then if you multiply this with the coefficient of variation per day, we will get maximum demand per day. So this is the peak daily flow. Then if you also multiply it with coefficient of variation per hour, you will get the maximum hourly demand in liters per hour. And if we divide it by 3,600, we will get the maximum demand per hour in liters per second, which is our peak flow, maximum daily peak flow in liters per second. So 45 liters per second. Then we have selected this part of the network, which is in total this amount of meters. So 2,446 meters. And now the software is dividing 4245 with this number and we have this specific demand in liters per second per 1 meter of the network, so 0.017350. And now this number is multiplied with each section's length, and we have a flow inside of a pipe. But in EPANET, and Hydra works with EPANET, to calculate hydraulic calculation, we don't need flows. We need water demands defined in the nodes. So if we now calculate the flows inside of each pipe, here we have settings. So these are the default settings, how to distribute the flows calculated to the starting and ending node of each section. The default is half to every node, but you can also go with all to starting node or all to ending node. I will leave the default half to every node. Okay, so here I will now just click on write. So write, and all the demands are now set to our nodes. So we have the specific demands in liters per second per 1 meter multiplied with the each section length, and then that flow is divided half to starting node and half to ending node. This is the method how to calculate this water demands using this method. Also, like I said, you can create multiple configurations. Let's add one more, and let's call this one, for example, tourists, or any other type of consumption category. Let's call it that way. And now you can again select the same area or some other part of the area. For example, additionally, just on these parts closer to the sea, we have some additional tourists, let's say. And here I will set water consumption per inhabitant. Let's increase it to 250. And the number of tourists, let's set to 1,500. Okay, let's leave everything as default, these parameters. And now you can see the maximum demand per hour is 1769. This is the total length of sections, and this is the specific demand. So let's click write. So now we have two consumption categories with different parameters. Let's also check some other options that we have here. Here you can see something that is called calculate by branches. So let's now check this. Okay, let's create another configuration of this same type of calculation, and I will call it by branches. We learned yesterday what are the branches. So branches are basically everything in between two main nodes. So branch, 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 branch. Okay, so if I click here, calculate by branches, but I will select the same part of the network as before. So this whole network, like this, you can see here, I didn't change this, so I will set it to have the same values as for the configuration for the people. So we had 180 here, and here we had 5,000. Okay, and let's now check it. So here you can see maximum demand per hour in liters per second is still 4245. Total section length is identical as before, and specific demand is identical as before. But now when I click write, so if this option is turned on, let's click write. Here you can see now, if you compare this column with this column, that it looks different because it is calculated by branches. So we have the water demands set only to starting and ending node of each branch. So why is that? Because as you know, in EPANET, you can have the, let's call them polylines, or links that consist of two junctions, starting and ending, and some vertices in between. In Urbano, we don't have polylines, but we have branches. So one branch can represent one multi-line pipe in EPANET. And basically, that's what we did here. So we distributed the same amount of flow, but just to the main nodes, and now this in between will be treated as one pipe. And you can see we have all other nodes in between are calculated as 0, because here in between we will have no demands. But if you summarize all these water demands, you will get the same value as for the people configuration. So that's how you can calculate this by branches. And also the procedure how to calculate it is basically identical. So you get the specific demand in liters per second per 1 meter, but now this is not multiplied with each section's length, but with the total branch length, and then that flow is divided half to starting node and half to ending node, but of a branch. Also, here you see something that is called corrected length of sections, or virtual length. So what is that? Let's also analyze what is that parameter. Let's do one more configuration, and let's call this virtual length. This is nothing but a method how you can basically redistribute flows. So on some parts of the network you have bigger flows, and on some part of the network you have smaller flows, but for the identical number of people. So if we go to settings, here you can see that you can define population density factor. And here you can see that by default everything is not defined, which is absolutely the same as 1. So if it is not defined, it's the same as 1. So let's now use our selection options, and let's select here, just on this last array, let's set population density factor to 2. And let's click right. Okay. For this array here, let's define 0.5. Okay, and let's click right. And for this in between, we will leave it as not defined, which I said is the same as 1. Okay, so if I select now the whole system, you see that we have some are not defined, some of 0.5, and some are 2. Okay, let's now go to our virtual lengths, and let's again select the same. So we will select the same area as in the 2 previous configurations. We will set water consumption per inhabitant to be, we set it to 180, and actual number of inhabitants, let's set this to 5,000. Okay, everything else will stay the same. We have 42, 45, we have this total length of sections, but we have now total corrected length of section is different. Why is that? Because now these section lengths here are multiplied with 2, and this section lengths here are basically divided by 2 or multiplied with 0.5. So basically what we did, we virtually increased the length of this section and we decreased the length of this section. And in the final result, we basically set that more flow will go to these nodes and smaller flow will go to these nodes. But you see the maximum demand per hour is still the same. So let's click right. Okay, for the virtual lengths, and let's now compare it. So here you can see that you can see all the configurations, all the values, but you see that the one that is selected in the tree is marked in this cyan color. So let's, for example, analyze this part of the network. So let's analyze people and virtual lengths, and you can see that virtual lengths are much bigger demands. If we select this array here, you see that virtual lengths in comparison to people are a lot less. And also, if we select these two, you see that they are still smaller because, of course, we had that number, number total virtual length is now higher number. So if we divided the same peak flow with higher number of section lengths, we will have the smaller this data for the specific demand. So if specific demand is smaller, multiplied with the same maximum demand per hour, we'll have the smaller virtual lengths, the smaller demands, even though all the parameters are the same and the population density factor stayed 1. So that's how all these calculations can work, and that's basically it. Okay, let's now go to settings, and let's set for the entire network this population density factor back to 1. So let's click right, and like I said, 1 is just like it is not defined, or you can click reset, it's completely the same. And also we have here one additional method, which is called inhabitants, but with Q specific. So let's add new configuration here, and let's select again the same parts of the network as before, these parts here. Okay, you see this is the total length of section, and total corrected length of section is now the same number. But now you can see that the software is not asking for number of people and consumption per inhabitant and so on. But the software is now asking for this specific demand in liters per second per 1 meter. So some of our users told us, okay, this method is really good, but we don't know the number of people. We don't know all these parameters here. We just get from some other guy who calculates all this. We have just this number. So now I will take just this number here, and I will go to this method. And here you can define it. So specific demand in liters per second per 1 meter of the network. Okay, let's set it, let's write it, and that's it. You basically have the same results as before. It's up to you, you know, which method you would like to use. But the thing is that let's check it like this. So if we select the whole network like this, and basically any of these data tables in Urbano, you can copy it. You can go to Excel or any other Microsoft application. You can just paste it, and here it is. So every preview functions that way. You can copy it to Excel. And let's now check this. So this is the tourists. This of course will not be the same, but if we check all these others configuration, let's sum this up. So if I sum the whole column, the total values should be equal to our peak hourly flow. Okay, so here we have that 42.45, and okay, 42.43. This is because of the rounding of the decimal places in the table. If we put to 6 decimal places, we will get the identical numbers. And the same is for this configuration here. So let's copy this one as well. So copy selected. Let's go to Excel. Let's paste it here. Okay, I will delete these columns. Okay, and let's do this. So you can see each time we get the same total hourly peak flow, no matter what method you are using. Okay, I will save this Excel as well to our day 2 folder, and or here to day 2, let's save it as demands. Okay, that's these types of calculations. Also, we have the method to directly set the water demands to house connections. So this is really precise and really detailed method, but it requires that you first draw the house connections. We will talk about drawing the house connections tomorrow. So, but just for your information, you can even define point demands or number of people living in each house connection, and then of course those demands defined in house connections can be distributed to starting node of a section, ending node of a section, or even here it is, so half to every node, all to starting, all to ending, or all to closer node, because a house connection can be connected in between two nodes. So that's also a method, but we will not talk about it. Also, point demands. Basically, point demands are the basic ways how you can define demands in EPANET. I will call it, we can call it, for example, point demand, or if this is some specific type of demand, for example, I will call it industry, but it can represent everything. And now you have your selection options. Just imagine in EPANET, if you want to define some water demands, you have to go double click on one junction, type something in. Double click on another junction, type something in. Here you can select any nodes that you would like to set something. And for example, all these selected nodes will have the same amount. So let's say 5 liters per second. And let's click right. Okay. And now we have 5 liters per second in each of these nodes. Or let's reset it. Now we can go also to directly in data table. And for example, here it will be 1, here it will be 2, here it will be 3, here it will be 5, here it will be 7, and so on and so on. So this is really nice, really easy method how you can quickly define water demands by using this point demands method. Let's again reset it, and I will just go to this one node, to this node here, and let's say here it will be some kind of industry that has the consumption of 6 liters per day. Okay, this will be for our example. Then we have firefighting demands, but you see that the firefighting demands are basically under point demands branch, which is basically just a type of point demands. So you can add a new configuration. Let's call it firefighting. And now you can see that you have input type. Input type can be direct input, which is basically exactly the same as the point method I showed you. So let's, for example, select some nodes. Let's select this node, this node, this node, and this node. And let's set, I don't know, 5 liters or 10 liters per second. Let's click right. And that's it. Or you can switch from direct input to proposal for firefighting demand. Then this is grayed out, and you have this calculation, which may not be suitable for the whole countries, but a lot of countries has this standard where basically the firefighting demand is in relation to number of inhabitants. So for example, for 1,000 people, you have one simultaneous fire. Minimum duration for firefighting is 2 hours, and proposal for firefighting based on this number of people is 5. Let's check what will happen if I increase it to 5,000. Okay, for 5,000 people, we have still one simultaneous fire, 2 hours, and now the proposal is 10 liters per second. Or if I switch to 10,000 people, you see that the proposal for firefighting demand is 15 liters per second. So if we click right, now you see that this proposed value is written to each node in selection. And also we have something that we call pipeline own demands, which are basically, this can be treated as some quantities of water that, let's say, the water company spends on cleaning the pipes or some repairments on the network and so on. And again, for the input type, you can use it like direct input and define point demand somewhere under a different consumption category. But the real way how this can be used is if you go here to calculate own demands for every node in percentage of the previously defined demands. So you can increase the total flows in the network, let's say by, I will increase it by 2%. So 2%. And now you have to select by which of the previously defined demands. But here, just for the purpose of this training, I defined a lot of this configuration, but in some realistic workflow, it would be, for example, people, tourists, and industry, okay? And I will select the whole system. And now this flows will be increased by 2% of sum of people plus tourists plus industry. And let's click right. And now you can see for each node, it is increased by this, this amount of flow. Or this can also be used, the same method can be used also if you want to increase the total flows, if you want to account the losses. For example, let's add another configuration. Let's call this water losses. Okay. And again, I will go to calculate own demands for every node. And here I will say 20% of all the flows, 20% of what? Let's say again, people, tourists, and industry. Let's take into this also into account. So let's write it. And now you can see this will also be taken into account. So this is 2%, this is 20% additional flow. So these are now all the methods. I showed you all the methods. So now you can see, okay, this is cool. This is something I should use. This is something I will not use. But now you know all the methods. And even though you didn't find anything you like, you can still import water demands from some external source. For example, from let's say Excel file or plain text file as well. Of course, we don't need all these methods here, so I will delete them. But before I delete them, I will save this drawing, so you have this as well, all these methods. So I will call this Hydra demands. I will call it like this, save. And then I will again resave it as working 2. Okay, do you want to replace it? Yes. Okay, and now let's go to our water demands. Let's delete the configurations that we don't want to use. So by branches, delete, virtual lands, delete, inhabitants with Q specific, delete, firefighting demand, delete, pipeline own demands, delete, and water losses, delete. So we will have people, tourists, and industry, and this will be our basic water demands to calculate this water distribution network. Okay, so now we have everything set to run hydraulic calculation. So we have this water tank here. We defined it. You can also see that you can have, by default, it's not showing here, but you can turn it on in your configuration. So let's go to our configuration of the profiles. This one here is the one that we use. Let's go to edit. And here under longitudinal section basic, you have something that we call decorations. And here you can include it in the drawing. And you can see that you can define, it says manhole type dependent, but it's really node type dependent, because if you don't include this, you will have the same block for everything. But I like this option turned on. And now under details, you can define custom block, different custom block for each of this equipment. For example, for emitters, for pumps, for reservoirs, for tanks, for valves, and so on. So where is the tank? Here is the tank. We will use this block. You can also use some custom blocks, and I will use the scale factor of 2, for example. So we will have a larger block here. Let's click OK. Let's click OK. And now you will see that the block for the water tank will also appear here in the profile.